Thank you very much for present me. Good afternoon for everybody. You see the title of my talk, Switchable Domains in Point Contact Based on Transition Metal Tellurides. My name is Naidyuk, and you see co-author of this talk. And co-author are from two institutes, Working Institute for Low Temperature Physics and Engineering from Ukraine, and Leibniz Institute for Festkörper and Werkstoffforschung, Dresden, Germany. Outline of my talk is, at first I tell you short introduction about transition metal dichalcogenides, and then I will tell a little bit more about specific properties of two dichalcogenides, molybdenum and tungsten ditellurides. Then I tell about observed resistive switching in point contact with this material. Then discuss switching mechanism and conclusion. So transition metal dichalcogenides were investigated intensively since the 1960s. In that time, around 60 TMD materials were known, at least 40 of them with a layered structure and weak van der Waals coupling between layers. The diversity of chemical composition and structural property phases of TMDs results in a broad range of electronic properties ranging from metallic or insulating state to the emergence of correlated and topological phases. TMD materials are highly attractive for fundamental studies of novel physical phenomena and for application ranging from nanoelectronics photonics to sensing and actuation at the nanoscale. Here is shown some small periodic table of TMD materials. In my talk, I will focus mainly on these two materials, molybdenum and tungsten ditellurides. They can be in semiconducting and semi-metallic state. They also display superconductivity. What is this? Okay, sorry. And recently, topological properties of this dichalcogenides was also predicted. So, what is interesting is these two materials that, for example, molybdenum ditelluride can exist as semi-metal and in a monoclinic form and orthorhombic form. This transition occurs at 240 K, and it's produce some hysteretic behavior in resistivity. So this first order phase transition. This transition is very sensitive to small amount of external perturbation, and for example, if we have not stoichiometric materials, so this deficit of, for example, tellurium, this phase transition disappears. Such transition is, first order transition is absent in tungsten ditelluride, but what is interesting in tungsten ditelluride is that after metallic behavior above 400 K, this metallic behavior in resistivity changed to the semiconducting behavior, that is resistivity decrease with the temperature. It was observed 6 years, about 6 years ago, and also was confirmed by recent publication in this by Yana. They observed minimum in the conductivity, which correspond to the maximum in resistivity. So explanation was that increasing conductivity above 400 K could arise from thermal excitation of carriers from the lower to the upper d orbitals. We investigate both compound by using Andreev and Janssen point contact spectroscopy before, and this data will be present in the poster after tomorrow. And in this study, we concentrate on the to look for the phase transition and such uncommon behavior of resistivity in these two compounds. So, and we try to look for this transition using also point contacts. So, a few words about what is point contact itself and point contact spectroscopy. So, point contact is represented usually as a theoretically as a hole in transparent for electron partition between two banks of between two metallic bands. If dimension of this hole is less than elastic and inelastic mean free path of electrons, then electrons move through this constriction by ballistic trajectories, and electron can be accelerated by applied voltage to the energy, which is equal charge times applied voltage. In case of diffusive regime, when the diffusive elastic length is smaller than the point contact dimension, there is diffusive flow in point contact, but if inelastic diffusive inelastic mean free path still is larger than point contact dimension, also electron can be accelerated to the maximal energy. Both of these regime are spectral regime. It's possible to investigate different mechanism of electron scattering in point contact. Another case is when size of point contacts is larger than the mean free path elastic and inelastic of electrons. In this case, all energy dissipate in point contact, and point contact can be heat up. So, for example, for standard metal with at fulfillment of Wiedemann-Franz law, temperature in point contact increases with applied voltage by 3K by millivolt. It means if you measure point contact at helium temperature, applying only 100 millivolts, you can heat up point contact up to room temperature. So we investigate, we use two kind of point contact by this investigation. The simplest procedure of creating point contact is to create mechanical point contact by touching of two pieces of samples. What here is photograph of the experimental setup. Here is small point is sample, and here is wire which touch these samples. In this way, it's possible to create point contact. And another way is to use so-called soft point contact. In this case, we place a small drop of silver paint on the samples, and in such case, it's also possible to create point contacts and measure its properties, electric properties. So here is shown differential resistance of point contact between silver paint and molybdenum ditelluride. We see that this characteristic show metallic behavior, that is differential resistance increases with voltage, and then we at higher voltage we observe such decrease in differential resistance, as I showed before, similar to decrease of the resistivity in tungsten ditelluride. So such change of differential resistance behavior from metallic to semiconducting. Such behavior for bulk samples of molybdenum ditelluride was not known, but there is such behavior for thin film of molybdenum ditelluride. It means that in point contact we see similar behavior to the in temperature dependence of resistivity. So in principle, this differential resistance of point contact reflect is similar to the dependence of resistivity versus temperature. So, but what is new, interesting, that at some point we observed such change of the resistance, and this change was reversible. It means when we measured at higher temperature, we observed such loop. Then this switching of point contact resistance from high resistance to the low resistance, and then restoring of this resistance again. We start to search such effect by different temperature and different point contact, and we observed more beautiful data of switching. When we start with low resistance state, then at some voltage we observed change of change of resistance to the high resistive state with semiconducting like behavior, and then at opposite voltage we observed switching back to the metallic low resistance state. So you see that by applying a voltage, we can change point contact resistance depending on the voltage. Such dependence exists also by increasing of temperature. Here is example of other point contact where instead of molybdenum, tantal iridium molybdenum is replaced by tantalum iridium, but this compound has similar properties to the structure for the molybdenum ditelluride, and here is shown the dependence of this switching effect on the temperature, and we see also that at room temperature this switching effect persists, only this sharp peak is smeared by the temperature. Also, this effect is enough stable. Here is shown switching effect measured for the tungsten ditelluride at room temperature. After 12 hours, we see reproducibility of this differential resistance behavior. And next slide is reproducibility of the switching effect during 1 week. So effect is observed at different temperature. It is stable, and so reproducible. So what is here is a statistic of the switching voltage. Switching voltage is different from contact to contact, but nevertheless it's in the range between 800 and 200 millivolts. And here is shown also samples for which we observed this switching effect. Additionally to the molybdenum and tungsten ditelluride, we observed this effect also for these 3 compounds which have the similar crystal structure, where molybdenum or tungsten is replaced by tantal iridium, or tantal rhodium, or tantal ruthenium. So with increasing temperature, this switching voltage decreased. It was also observed, and also amplitude of the effect also increased by temperature, but nevertheless, as I showed before, this change of resistance even at room temperature can be 2 orders of magnitude. Now we start to, after we observe such switching effect, we start to thinking about origin of the switching. So during this thinking, we paid attention to several papers where ferroelectricity in molybdenum and tungsten ditelluride was discussed. So in paper published by Yuan with title Room Temperature for Electricity in Molybdenum Ditelluride down to the atomic monolayer limit, they concluded that origin of the electricity results from the spontaneous symmetry breaking due to relative atomic displacement of molybdenum and tellurium atoms. In the next paper by Fei, with title Ferroelectric Switching in Two-Dimensional Metal, they found that 2 or 3 layer tungsten ditelluride exhibit spontaneous of-plane electric polarization that can be switched using gate electrodes. Moreover, the polarization state can be differentiated by conductivity, and the carrier density can be varied to modify the properties. These 2 papers investigate monolayers and few layers samples, and Sharma investigated bulk samples of tungsten ditelluride with title A Room Temperature for Electric Semi-Metal, and they concluded that bulk crystalline tungsten ditelluride exhibit stable polarization states that are switchable under the external electric field. Thus, ferroelectricity is a bulk property of tungsten ditelluride. Taking this paper into account, we came to idea that when the relative atomic displacement of molybdenum or tungsten atoms and tellurium atoms produce polarization, in other words, electric fields, then inverse effect must also take place. Namely, high electric field in point contact can induce mentioned atomic displacement that leads to the new phase formation and appearance of electric domain in point contact with different structure and properties. So, in conclusion, we observed resistive switching in point contact based on series of TMD compounds such as molybdenum tungsten ditelluride and tantal rhodium ruthenium iridium ditelluride. The effect consists up to 2 orders of magnitude change in the point contact resistance, what increases with lowering temperature. The origin of the effect can be reversible modification of the crystal structure of TMD in point contact under applying of high electric field. Here is shown a model that which the largest electric field is in the point we can induce in the point contact, and this region under strong electric field can be switched by using of applied voltage. So we state that such common and consuming PC method has a big advantage in finding suitable materials for application. By using modern nanofabrication technologies to form such structure, the device parameter can be vastly improved. Our observation of the switching effect in the series of TMD compounds expands significantly the range of materials suitable for resistive random access memory application, ferroelectric phase change transistor, and other nano and optoelectronic application. Additionally, I would like to say that also interesting because all this molybdenum and tungsten ditelluride can have some topological properties which modified surface electronic states that it will be interesting to it will be interesting to explain this switching effect on microscopic level, that is taking into account this topological surface properties of these materials. Thank you for your attention.
As far as I understood, you used the in-plane contact geometry with the current flowing along the C direction. Am I right?
Generally, yes. But it's difficult to know what is the direction of current in point contact, because this surface is not atomically flat. So probably there is also some steps. The current can flow not only in C direction but also in B direction. But nevertheless, it's effect present.
Thank you.
Yurii, I was completely unaware of this behavior of these tellurides, but does it pertain only to tellurides, or do you have an idea also about, for example, selenides or some other compounds?
So it's, I don't know which. We checked this for 5 materials which semi-metallic behavior, and for these materials we expect these ferroelectric properties. Probably if selenide also have, I don't know, probably not all selenides have semi-metallic behavior, mainly semiconductor behavior probably, but it's interesting to check.
Yes, please.
So interesting phenomenon. So same question I had what was already asked. So maybe different one. So the trick is point contact, because in the point contact you have a large electric field, a large gradient of that. Did you try to evaluate the size, some values of the electric field which you can achieve there?
Yes, for several point contact we evaluated size, and size is of the order of a few hundred nanometers, and estimated electric field, lower value of electric field is 10 kilovolt per centimeter. And probably in general it should be larger, because if we suppose that we have one point contact, in the case of soft point contact we can have several point contact. In this case, electric field for smaller point contact will be even larger. So,
are there any measurements? I mean, geometry on atomic layers where people can give some numbers. If this your kilojoules per centimeter is enough, or is it big or small number? You want to have this ferroelectric effect. Is it enough? This kilojoules per centimeter.
in principle, yes, there are similar experiment on nano bridge, yes, and the electric field is of the same order.
Is there any question? Yes. Thank you, Professor.